Hello everyone, this video will be presenting a short demonstration for Tenclave. This application is designed to help energy communities manage and monitorize energy-related data through private and secure computation. This was achieved with the implementation of programmable cryptography, as well as encouraging better energy flexibility through its members and resolving a battery output optimization problem. This has been achieved enabling different modules in order to combine zero-knowledge proofs and fully homomorphic encryption with a proper display and data management, all in the same platform. To access the application, there is a login system that defines by role what the user can be accessing. A common member will have access to his own energy data only, whereas the administrator will have access to all the data. Transactions and proofs of blockchain operations will be displayed for everyone. When the login is successful, the functionalities appear for the user to interact on the navbar. The dashboard presents all relevant data and analysis related to energy consumption, production, and battery usage, displayed on an hourly basis within the selected time frame. To improve clarity and usability, consumption was decided to be divided into 3 distinct categories and assigned a representative color for its meaning. In green, the energy consumption that falls under the generated energy from the community. In red, the energy consumed over that generated energy. And in blue, the surplus, energy that is wasted but is compensated, which seems neutral. It's also represented visually through a radial chart that highlights the total consumption for the selected period in an intuitive way, so users can have a general idea with the performance in a glance. The production section illustrates solar energy generation, distinguishing between energy directly injected into the grid and the portion allocated to the user based on the community-defined coefficient. In parallel, the battery visualization shows charging periods during a day and a consistent discharge pattern during nighttime hours. Additional information elements are included for users who wish to explore the data in greater detail. For our next core functionality, there has been a ranking system set to incentivize users from 2 approaches, as they are being rewarded with tokens for their energy flexibility whenever they consume around 20% of the available energy through zero-knowledge proofs, and to compete between the rest of the members to see who can obtain most per time periods and such. As we can see above the ranking table, we can check all the blockchain transactions where tokens were given. We can see the proof, the hash transaction, the date, and the amount of tokens that were given. We have still not defined what the token value should be, but we're testing the waters on whether there should be watts discounted at the end of the month in the bill or something that way. The last functionality covers an optimization problem that was caused by the incapability to operate sensitive users' data to manage the battery output. With the fully homomorphic encryption, we are able to compute encrypted consumed values from the energy community members. This helps obtaining the necessary output the battery could make to compensate possible deficits for times the energy available on the net is not enough. Here we have displayed a table where we can see all the blockchain interactions that the fully homomorphic encryption have computed to obtain battery output. We can see reflected the transaction hash, the result, as well as the date.